The Beer-Lambert law connects three critical parameters: absorbance, concentration, and path length. At its heart, the Beer-Lambert law states that the absorbance of light by a substance is directly proportional to both the concentration of the substance and the path length of the light beam through it. This means that a higher concentration or a longer path length results in greater light absorption. As concentration increases, more molecules are available to absorb light, which leads to higher absorbance values. The path length of a cuvette, like the ones shown here, directly affects absorbance. Longer path length means more opportunity for light to interact with the sample. When light passes through a sample, some wavelengths are absorbed, transmitted, or reflected based on the sample's properties. Understanding this relationship between absorbance, concentration, and path length is crucial for quantitative analysis in spectroscopy. The Beer-Lambert law is mathematically expressed as A equals epsilon times L times C. Let's examine each component of this formula. A represents absorbance, which is the amount of light absorbed by the sample. This diagram illustrates how the Beer-Lambert law works in practice. Light passes through a sample in a cuvette with length L, and the absorbance is measured. Epsilon, the molar absorptivity coefficient, represents how strongly a substance absorbs light at a specific wavelength. Each compound has a unique epsilon value. The path length, L, represents the distance that light travels through the solution, typically measured in centimeters. In a standard spectrophotometer, this is the width of the cuvette. Finally, C represents the concentration of the substance in solution, typically expressed in moles per liter. As shown here, varying concentrations of a colored solution will absorb different amounts of light. When both epsilon and path length are constant, the Beer-Lambert law shows that absorbance is directly proportional to concentration. This linear relationship is fundamental for quantitative analysis in spectroscopy. In summary, the Beer-Lambert law formula, A equals epsilon LC, establishes the mathematical relationship between absorbance, molar absorptivity, path length, and concentration. This equation forms the foundation of quantitative spectroscopic analysis. The Beer-Lambert law has numerous important real-world applications that demonstrate its practical significance. In medical diagnostics, pathology laboratories use spectrophotometers based on the Beer-Lambert law to analyze blood samples. One critical application is measuring bilirubin concentration in blood samples to diagnose liver function and detect conditions like jaundice. The test relies on measuring light absorption at specific wavelengths, typically 546 nanometers for bilirubin, using specialized equipment. Environmental scientists also rely heavily on the Beer-Lambert law to monitor pollutants in air, water, and soil. UV-VS spectrophotometry allows scientists to identify and quantify various contaminants by measuring their characteristic light absorption patterns. This technique is vital for monitoring water quality, detecting air pollutants, and analyzing soil contaminants to protect public health and the environment. The applications of the Beer-Lambert law have evolved significantly over time, expanding from basic laboratory measurements to sophisticated medical and environmental analyses. Beer-Lambert's law continues to evolve with recent advancements in spectroscopy. Traditional Beer-Lambert law assumes linear absorption, where absorbance is directly proportional to concentration. This is represented by the classic formula A equals epsilon LC. In linear absorption, light waves interact with molecules in a consistent manner regardless of intensity. However, nonlinear spectroscopy introduces intensity-dependent absorption, where the behavior changes with light intensity. Another significant advancement is in multi-component analysis. This approach allows us to analyze mixtures with multiple absorbing components by measuring absorbance at different wavelengths. For example, when analyzing a mixture of two drugs, we can determine the concentration of each by measuring absorbance at two different wavelengths. These advanced approaches expand the applicability of Beer-Lambert's law in developing new materials for lasers, analyzing pharmaceutical mixtures, and monitoring environmental pollutants. The Beer-Lambert law is evolving through integration with modern technologies. Machine learning algorithms enhance the predictive accuracy of spectroscopic analysis based on Beer-Lambert principles. Smartphone-based platforms use machine learning to analyze spectral data from bodily fluids, significantly improving medical diagnostics. The Beer-Lambert law is also being applied in miniaturized microfluidic systems for on-chip chemical analysis. These systems enable precise measurements of light attenuation through both homogeneous and non-homogeneous materials, following modified versions of the Lambert-Beer law. Advanced spectroscopic applications expand the utility of the Beer-Lambert law across diverse fields. Hyperspectral imaging from drones uses Beer-Lambert principles to analyze surface reflectance, while modern spectrometers provide increasingly accurate measurements. Machine learning models extend the traditional Beer-Lambert equation by incorporating complex spectral features, allowing for more accurate analysis even when traditional limitations are present. The Beer-Lambert law continues to evolve with new modifications and techniques to address its limitations. To address the limitations of the classic Beer-Lambert law, especially in complex media like biological tissues, scientists have developed the modified Beer-Lambert law. This modified formula accounts for scattering effects by introducing a differential path length factor and a scattering term. This allows more accurate measurements in tissues where light scattering is significant. The modified approach specifically addresses key limitations of the original law. These include nonlinearity at high concentrations, light scattering, and other factors that affect accuracy. Modern advancements in spectroscopic techniques have extended the applicability of Beer-Lambert's principles. These include time-resolved spectroscopy, surface-enhanced spectroscopy, photoacoustic techniques, and ultrafast methods that can capture dynamic processes. Machine learning is revolutionizing how we analyze spectroscopic data. AI algorithms can detect patterns and relationships that traditional analysis might miss. Machine learning integration offers several key benefits: enhanced accuracy in analyzing multiple components, automatic detection of nonlinearities, and real-time analysis of complex mixtures. The modified Beer-Lambert law is particularly valuable for analyzing biological tissues, where light scattering is a significant factor. Applications include monitoring brain tissue oxygenation, cancer detection using optical spectroscopy, and non-invasive glucose monitoring for diabetic patients. Looking ahead, we anticipate several exciting developments in how Beer-Lambert principles will be applied. These include combined optical acoustic approaches, quantum computing for complex analysis, miniaturized devices for point-of-care diagnostics, and integration with other imaging techniques. Despite its limitations, the fundamental principles of the Beer-Lambert law remain essential. With these modifications and new techniques, it will continue to be a cornerstone of spectroscopic analysis for years to come.